Good
Hey,
morning,
Rebecca.
everyone. Oh,
Hi,
hey,
all.
good morning. Um, Welcome to our Storage Innovations 2030 Prize winner pitch sessions. Before we get started, just a few housekeeping things. Each team is going to have 5 to 7 minutes to present their technology. I know it's black. It's going to be fine. And this is being recorded and will be shared on the HeroX website. So just be conscious of what you share. And we're looking forward to learning more about all of your technologies. I have all the slides here and I'll be advancing them. And all right, let's get into it. Oh, you know what? I don't think we have sound, do we?
No sound.
Oh no. All right. We're gonna skip the video then. Okay, here's our agenda for today. So we have Ben's gonna give a quick introduction and then we'll go through our champion and finalist teams. Okay.
All right. Well, good morning or good afternoon if you're on the East Coast to all. I'm Ben Schrager with DOE's Office of Electricity. I have to join from my phone right now because my computer picked 11:58 a.m. to update, and I could not push that back. So hopefully I can join my video on in a few seconds, but I'll give a quick introduction. I just want to say a huge, sincere congratulations to all of the winners on this call and those who couldn't make it, to all 10 winners of our Storage Innovations in prize competition. I think I mentioned this on Monday. This was our first ever storage prize, so this is a really big deal. And the fact that we even have enough exciting, interesting storage innovations to run a competition like this, I think speaks volumes to just how exciting the whole field of long duration energy storage is. So again, huge congratulations to everyone. This is a really exciting time. So I'm going to give a quick introduction, but it's really going to be about hearing from you today. I'm really excited to hear all of our pitches. We obviously reviewed all of your proposals, and we're aware of sort of what you guys proposed, but hearing you talk and hearing you present through it today will be really enlightening as well. So we talked through this on Monday a little bit. This is the long duration storage slide, practically required to have in any deck like this. But this is sort of our key goal, to reduce the cost of energy storage by 90% for long duration, 10 plus hours duration energy storage this decade. So this is really our key driver for the Storage Innovations Prize competition, as well as a lot of our activities right now, is really pushing hard towards this aggressive cost goal. If you go on to the next slide. Right, so you could just click ahead a couple times to show off all the different pillars here. So this is our sort of central strategy for Storage Innovations 2030. The prize fits in again, this was our first ever prize to competitively evaluate and explore some of the most exciting, emerging, or innovative energy storage technologies. So this was really our opportunity to get a sense of all the really exciting innovations that are out there, and do so to complement the other parts of Storage Innovations, the framework and the flight paths. So all three of these efforts will be part of a future report that is going to Congress later this year, a report that's highlighting energy storage innovation. So I think the next slide has more information. If you click ahead. Yeah, so this is our report to Congress requirement. So periodically, Congress will ask DOE or any government agency to write reports on various different topics that are of interest. So in this particular case, we are instructed to publish a report on emerging energy storage technologies, including an analysis of which technologies show promise for further or future funding. So the key analysis piece of this report will be coming out of the framework and the flight paths. And we've highlighted a set of technologies that's listed on the Storage Innovations website that we'll be delving into as part of the framework and the flight paths. But we really wanted to include the results from the prize competition in this report, as a way to highlight our winners and to show off even more exciting and emerging innovation in the field of long duration storage. So this is really our opportunity to have one section dedicated to the prize winners, and to feature them in the report in this way. So as a reminder, this is a report that will be sort of going to congressional staff. This is something they asked for, and will be released publicly as well. So we hope it's a good opportunity for visibility, and just one more sort of incentive that you guys get for successfully winning or being a finalist in the prize. So, the only reason we've been pretty non-committal so far with our language, the review process for these reports pretty extensive, and so there is a chance, there's always the opportunity that someone higher up could say that we have to cut sections or cut the prize section, right? So we can't guarantee inclusion, but I sincerely hope to include a section on the prize. If you would like, and if you would like to opt out of being in the report, that's also completely fine. And that's something that we can certainly accommodate. So we'll be writing up short blurbs on each winning technology to include in the report, largely from the content that's shared today. So we may come back to you just to make sure that any language we include about your technology is acceptable. They'll be fairly short, fairly high level, but just again, we really want to include this opportunity to show Congress, show the public, like there is more exciting innovation. Look at these 10 technologies as a really great snapshot of this innovation. So I think that covers most of the details. Again, there'll be more formal instructions and direction to come, but I just wanted to give this preview. This might explain a little bit of that sort of non-committal language and why we can't 100% guarantee inclusion, but why we're also saying that you can opt out. So it's really about what you want and what we're able to do. So one more exciting opportunity. And then if you go on to the next slide. Yeah, so I'll just review again the prize. This was part of the American Made Challenges Network, which has sort of a lot of great, many great clean energy prizes, dozens of prizes, hundreds of network members. It's a really great program to run a prize under. Then click ahead once more. So yeah, we talked about all of this. What is the Storage Innovations Prize? I think at this point we're all pretty familiar. And so I just want to again highlight that this was a really exciting opportunity, and we saw some really great innovation from our winners and from all of our submissions as well. So we selected 5 Storage Innovations champions to receive $50,000 each, 5 Storage Innovations finalists to receive $10,000 each. Those were announced on Monday and just can be shown one more time on the following slide. Huge congratulations. This was a rigorous judging process, and the 10 of you rose to the top. So really have some of the most exciting innovation to our DOE and National Lab expert judges. So I think that's all I have. I'll turn it back over to Rebecca to facilitate the sessions. Thanks all.
All right, we're going to kick things off with Electrified Thermal Solutions.
Thanks, Rebecca. Hopefully everyone can hear me okay.
Yeah.
All right, then we can jump right in. So as mentioned, we are Electrified Thermal Solutions. Really pleased and happy to be here and happy to have won this prize. Thanks for the opportunity. We are decarbonizing industry with renewable heat. We can jump right in. So the market pain that we see is that there is no affordable zero carbon heat option for industry today. The good news first, if you dig into that, is that renewable electricity is really cheap, but there's really 2 challenges with it. One is that storing it for later is expensive. And we will need to do that because we need constant energy. The other challenge is that industries really need heat, often high temperature heat, not electrons. So we need to solve the firming issue, and we need to solve the conversion to heat issue. And that's what we do at Electrified Thermal. So our solution is the Joule Hive thermal battery. We turn intermittent renewable energy into industrial grade heat. When we say industrial grade, we mean really hot, up to 1800 Celsius, basically hot as flames. We can do this far cheaper than, say, green hydrogen, and we can, best of all, retrofit this system into existing processes and plug in due to our flexibility and simplicity. So the Joule Hive itself sits at the intersection of the electric power input. It could be a wind farm, solar farm, nuclear plant, hydro plant, or just the grid itself with electrons on it. We take that power in when it's cheap or available, we convert and store it as heat in the Joule Hive, and we give that heat to an industrial process in the form of a hot gas. It could be air or another gas that we can use to run your boiler, your furnace, your kiln, or even your power turbine to return it back into electricity if needed. Next slide, please. Now, the way we do this and the way we do it affordably is really 10 years in the making, mostly at MIT during my time there, which was that we developed electrically conductive bricks that can be stacked up to the gigawatt scale. So when we looked at the problem, roughly 10 years ago, of how can we conveniently turn electricity into heat, because this electricity is getting so cheap, what we basically ran into is that existing materials aren't great at doing that. They burn out frequently. They're not really up to the task of solving industry's challenges at the really large scales. So what we did was we started with materials that can withstand the temperatures, and we asked ourselves, can we turn those into electric heaters? So these bricks here on the screen, there's my hand for scale. These are now being mass produced with one of the largest refractory suppliers on the planet that we're working with. These are electrically conductive bricks. We basically turn these bricks into electric heaters. They melt well past 2000 Celsius. And we could basically stack those up, as you can see on the screen here, into big form factors of electric heating systems that could fill out, say, a shipping container or a tall vessel, such as those hot blast stoves shown on the bottom. And so they electrically heat up as a giant electric heater. They are a giant thermal store that hold that electric heat for later. And there's air channels in there that operate as a big heat exchanger. And so all in one box, we have electric heating, storage, and heat out in the form of a heat exchanger that is well integrated and cost effective. And if we go to the next slide, we could show some scalability here that, right now we're piloting a system that's roughly the size of an elevator in our lab in Medford, Massachusetts. But we can scale this up to many megawatts. The first units we're planning are 2 to 5 megawatts out, holding roughly 25 megawatt hours. And that shipping container model that we're showing, that's our first product. You can easily install multiple of these on a site. And from there, we can go tall in the tower kind of vessel formulation we're showing here, even up to the gigawatt hour scale and hundreds of megawatts out. And you can even have multiple of these on a site. And if that sounds ambitious, to the right there is sort of our inspiration for this tech, which is hot blast stoves. These are giant towers full of bricks today that are storing waste heat. So we're going to leverage and mimic things that they've done to hit these scales. Though in the meantime, we'll be doing shipping container units that are easier to do and very valuable in the interim as we work our way up. Next slide, please. Now, if we talk about where we kind of sit from a competitive edge perspective, the Joule Hive technology, our patented oxide bricks here, they're hotter, cheaper, and more scalable than what we see out there today. I mentioned this is a long time in the making. We didn't start at this. We started by looking at what's available today, and we looked at traditional metallic heaters, traditional ceramic heaters. What we found is that these are either not very scalable and expensive because they burn out frequently, or they're not hot enough. For the really high temperature industries such as cement, steel, glass, ceramics, or to run power plants that need the higher temperatures for the better efficiencies. So our bricks are a few $1,000s a ton. You need to pay a few $1,000s just for a couple of heater elements of those ceramic heaters. And if you look at to the right more, you see that graphite, for example, it burns out. So it has a hard time getting its heat out if you're in anything other than an inert environment. So it's not very good at giving the high temps either to industrial needs. And finally, all the way on the right is hydrogen, which is very, scalable, very high temperature, but very, very expensive. We're bringing something genuinely new to the table with this material breakthrough that lets us hit high scalability, low cost, versatile in its operation, and high temps. Next slide, please. So just a quick snapshot of our team. We have roughly 40 years experience on the leadership team across technology R&D, product development and scale up, and business development in the energy space and the grid edge. And our advisory board is full of expertise in upstream and downstream needs of supply chains and industrial needs for the high temperature sectors, and experts on regulatory and fundraising and entrepreneurship. So we're a growing team that's ambitious. And I'll end with our final slide here, I believe final slide, which is just our vision, which is to have a Joule Hive in every furnace, boiler, and power plant fully decarbonized by 2050, which is roughly a $3 trillion market that we would be touching there, which is what we spend on fossil fuels today. So it's an immense problem, and we appreciate the support and the help of DOE in this. I think that's it. Thanks very much.
Great, thank you so much. I just want to add here that since these are pretty quick pitches, if people in the audience would like to ask questions, there's a Q&A box, and our panelists can go in and type out your answers, respond to those as you see fit, the ones that are directed at you. Great. Our next is RCAM Technologies, RCAM Technologies.
Great, thank you. Yes, so let's go to the first slide. Okay. Yes, so I'm Jason Cottrell, founder and CEO of RCAM Technologies. We have offices in Los Angeles, Colorado, and in Scotland. Today, we'll be discussing our marine pumped hydro energy storage system, which is basically a form of long duration energy storage at the bottom of the sea. Let's go to the next slide. So as most of us are aware, the majority of Americans, about 40%, live in the coast, the big cities like LA, Florida, Houston, and so on, in less than 10% of the landmass. And these cities need power and they need storage if they're going to use renewable energy forms of electrical generation. Let's go to the next slide. So accordingly, the US is really counting on the use of floating offshore wind and regular offshore wind on fixed bottom to provide this electrical power. Now, this power needs energy storage in order to deal with what is one of the most variable forms of renewable energy. So there's been quite ambitious targets set over the past year and even this year. So the White House set a 30 gigawatt offshore wind target by 2030, and then 15 gigawatt target by 2035, primarily in deeper water. And in the bottom right-hand corner, you can see what that looks like. Each one of those black boxes is a potential offshore wind plant of typically hundreds, at least hundreds of wind turbines. And all of that power has to be integrated into the grid, and most of it tends to be near these high density areas. That creates electrical challenges with interconnection, grid stability, something that is called the wind doldrums. What do you do when the wind dies? And then the opposite problem is when you have too much wind and not enough load, it can result in curtailments. So if we go to the next slide. So that's where we come in with what we call marine pumped hydroelectric storage. It's a type of energy storage that can be co-developed with these floating offshore wind plants. Now there's some specs on the right-hand side. It has a lot of benefits and features, both technically and from a jobs and diversity, equity, inclusion. These are concrete spheres at the bottom of the seafloor that are manufactured in US ports, many of the ports which are near these large population centers. So let's go to the next slide. So to understand the operating principle, it's essentially the same operating principle as conventional pumped hydroelectric storage, which is one of the largest forms of energy storage in the US. At over about 93% of our energy storage comes from pumped hydroelectric. Basically, what we're doing is we have large diameter spheres, 20 to 30 meters in diameter, at the bottom of the seafloor, and we pump the water. We allow the water to flow in to generate electricity, and we pump it out to serve as a battery and store that electricity. So what we're basically doing is taking the best part, as illustrated on the left-hand side diagram of conventional pumped hydroelectric, and we're integrating that and using that at the bottom of the seafloor. And what that gives us is a relatively small footprint and the ability to install this energy storage where you need it. So if we go to the next slide, and hopefully, well, that's just showing the charging and discharging process. Let's go to the next slide. Now, this is really not that far out of an idea, The technology was started to be developed by the Fraunhofer Institute and jointly by MIT in around 2012, 2014. And Fraunhofer has deployed a small scale, 1/10 scale sphere in a 100-meter lake in Germany and connected it to the grid. So it's relatively low risk. And if we go to the next slide, the question is, well, what are we bringing to this? So what we're doing is we're industrializing the system and bringing some new innovations to create what I would call a second generation subsea energy storage system. Those innovations are the use of 3D concrete printing to reduce the largest cost element of the system, that is the concrete spheres. So we automate that process, increasing production rate, and reduce the footprint of this system manufactured in the ports. In addition, the second thing that we do, and that's fine, we can stay here, is we're adding multiple spheres to the system. What that allows us to do is increase the capacity of the system. It gives us options, so we can increase the length of storage by adding additional spheres while keeping one single generator and pump turbine assembly. And then the third thing we do is we integrate it with offshore wind. There's a number of synergies that we obtain, cost reducing synergies, such as sharing the subsea cable to shore, the operation and maintenance systems, the manufacturing and supply chain with those offshore wind systems. So to wrap up, what we have here is some new options for energy storage that are completely untapped at this time. It's hidden, it has no effective onshore footprint, relatively low cost and low risk, and it's locally manufactured with readily available concrete materials and uses seawater as its operating fluid. In addition, it's immune to weather and supply disruptions because it's relatively stable there at the 750 to 1,000 meters that we install this at. But this is still a tough technology. It takes government, both public and private investment to develop these, to demonstrate these. And that's primarily where we're at today. We're working on scaling up and creating pilot projects that we can deploy right off of Los Angeles by Catalina Island to do the testing. And the next step after that is the grid connected testing at a site to be determined. So thank you for your time. My email address is there. Feel free to reach out if you have questions or interest in collaboration.
Great. Thank you so much for your time.
Thank you.
Our next winner is Gravity Power, LLC.
Hello, everyone. I'm Jim Fisk of Gravity Power. As most of you already know, that the vast majority of stationary energy storage currently is pumped hydro. And it's an excellent solution, except for the difficulty in building new plants. In 2009, there were 43 pumped hydro plants in the FERC queue. And as of this date, not one of them has been constructed. We have to build storage much faster than that in the future. Next slide, please. Our solution is to build a new type of pumped storage hydro, which starts with a conventional powerhouse, totally conventional pumped hydro powerhouse. Adjacent to the powerhouse, we excavate a very deep shaft. In that shaft, we put a steel-lined piston made mostly of rock and concrete. We have a conventional penstock connecting the powerhouse and the shaft, and fill the whole thing with water. This gives us a very tiny footprint, but in operation, it functions exactly like pumped hydro. The pump turbine pumps water out of the top of the shaft, forces it down the penstock, and hydraulic pressure elevates the piston to store energy. To get the energy back, the piston is allowed to descend in the shaft, forces water back through the turbine to generate electricity. Because we have such a tiny footprint, we have almost no environmental impact. And because of the operational efficiencies of the system, we have significantly higher round trip efficiency than even pumped hydro. Because of the piston operation and hydraulic physics, pressure is constant to the pump turbine, which provides operation at the best efficiency point. Next slide. Construction uses all conventional equipment, road headers, drilling equipment. Vertical conveyors allow us to remove cuttings from the shaft with high efficiency, and almost all of the equipment involved in construction can be electrical equipment, which removes CO2 emissions that would be required during construction. Large shafts of this type have been built all over the world, although perhaps not quite as large and as deep as ours. Next slide. Project metrics, piston diameter ranges from a little under 30 to almost 100 meters in diameter. Shaft depth is 500 to 1,000 meters. And the piston is always 1/2 of the shaft depth, 250, 500 meters. And for people who who are not familiar with hydraulic physics, they get interesting ideas about how much pressure is required to lift the weight of the piston. In our case, because the piston is so large, we can use large in terms of cross-sectional area. We can use relatively modest pressure to lift a massive weight. In a very large gravity power plant, we can lift several million tons using totally conventional pressure from pumped hydro. At a 500-meter shaft depth, we're only getting 375 meters of head, which is kind of right in the middle of pumped hydro ranges. With a 1,000-meter depth shaft, we get about double that, which is still in the range of conventional pumped hydro. But as I said, up to 5 or 6 million tons of weight can be lifted with this methodology. Next slide. We have some world-class industry partners. Babenderde Engineering from Northern Germany helped us with our original designs. Freudenberg Sealing Technologies provides the technology for our piston seals. Stantec has designed pumped hydro plants for installation all around the world and is quite excited about adding this to their capabilities. And Robbins Company, who invented the tunnel boring machine, is helping us with excavation machine technology. Next slide. So our mission is to beat the long duration storage shot LCOS goal of 5 cents per kilowatt hour before 2030. And we think we can beat that by a significant amount. And then to provide an achievable pathway to massive grid decarbonization. We'll be making some significant announcements in the next few weeks. So please follow us on LinkedIn. Thank you for your time.
Thank you. And just a reminder to our panelists that we have a couple questions. All right, Kinetic Core Solutions.
Yes, ma'am.
Hello.
All righty. Well, thank you guys for the opportunity to come and do a presentation. And we are very excited to be part of the team here, getting some pretty amazing ideas out there for practical implementation. And we are kind of bringing that into play here as well. My name is Dr. James Cleghorn. I'm the president and founder of Kinetic Core Solutions. And what we are focusing on are cost-effective, safe, and green capabilities as an alternate for short and long-term deployable energy storage. So with that, if anybody wanted to chat with us, our email and website was on the front page, at least the website's right there. Thank you. But going ahead, one of the biggest problems that we are tackling here with the Energy Grant Storage Program with DOE is the increasing amount of renewables being integrated and the modernization we need to do with the grid. It requires abundant energy storage. I think all of the folks presenting here will agree with that. We have great solutions, that long duration storage is a challenge, basically being able to put it into all the different environments. With regard to locations and temperature, how close you can get it to the folks that need the storage, how you can get it deployed, even providing the power to move and transport that over the the grid itself, being able to get your storage close to where you actually need it applied. So what we're looking at is, what if long duration had another competitive option? And that's what all of us are kind of bringing forward in these presentations. Next slide. I'd like to introduce you to is the Kinetic Battery. We are a next generation flywheel, all composite. It's designed for a 25-year life. The advantage is we have unlimited daily charging cycles because we have no chemicals in our system to wear out. We use a large assortment of commercial subsystems that allows us to reduce the risk of our deployed system. And the advantage is that we are a modular unit designed for 50 kilowatt hours with a smaller power electronics unit to allow you to do between 5 and 25 kilowatts. This provides you a wide operating region from 2 hours of higher power to 10 hours of longer duration power. Each one of our modular units is a very small footprint. You're talking about a 5 foot by 5 foot that can be put in rows and being able to be scaled up to whatever is required at the customer's site. And the other advantage is that we can be deployed essentially anywhere. Our temperature range is -40 to 120 degrees Fahrenheit. So we can be deployed in cold regions, hot regions. The battery itself just doesn't care. It doesn't change our performance. Next slide, please. So what is our innovation that we are bringing forward? Well, flywheels have been around literally for 2,000 plus years. And modern flywheels all hail primarily from the Industrial Revolution of about 200 years ago. What we are bringing forward is another evolutionary jump. We commonly refer to that, we're just not your grandpa's flywheel. If you notice, the traditional flywheel on the bottom left is a cylindrical design. It's primarily focused on, if you need more energy storage, you add more mass. So a traditional flywheel for 50 kilowatt hours is about 5,000 pounds. If you take a look at our design, we use a 3D curvature shape. So we are essentially an ellipsoid. It allows us to do much higher speeds than a traditional flywheel. Therefore, for the same storage capacity, we don't need as much mass. And mass is directly proportional to how much the unit costs, which allows us to bring down the overall cost for the next generation of flywheels that we are bringing forward. So our flywheel on the right-hand side, that's what it looks like. We come in at about 500 pounds for a 50 kilowatt hour capability. What this allows us to do is have much safer operations, very low parasitic losses, and we're made out of steel and carbon. We're fully recyclable. Next slide, please. So our value proposition is what we kind of look at, taking a look at what current chemical batteries are out there and how we can help out with the long duration and actually having a lot of flexibility in how we could be operated. We have a low deployed cost and a very small footprint, but one of our biggest advantages is the ability to have unlimited uses per day, which is very uncommon for the chemical sides, the traditional chemical batteries, because they wear out too fast. We do not have that limitation. So we have essentially 0 battery replacements over the course of 25 years. And looking at the levelized cost, we can be up to 7 times lower cost than our chemical battery brethren. Our efficiencies are also very high. We're very much on par with lithium. And you have the advantage that we can operate essentially anywhere the customer needs to have energy storage deployed. And the improved safety, we don't catch fire, we don't explode, and we have no hazardous materials built into the system with regard to how we store the energy. Next slide, please. So a quick overview and summary. Really, lithium ion is the current primary long duration battery with regard to deployed chemical systems, but it has a projected shortfall by about 2027, according to the US Geological Survey. We just don't have enough of the chemical batteries, specifically lithium ion, to meet the demand that we're looking at. Our kinetic batteries provide a very cost-effective but non-chemical alternative. We have no rare materials. We have a constant level of performance over the entire life cycle of the battery. We're small and have a very deployable footprint, and we have the improved safety aspects that worry a lot of the folks that are looking at some of the chemical systems being deployed. And the chart to the right-hand side just kind of gives an idea of what the global demand we would be helping out with, because we'd be looking at the stationary storage applications that normally are being used with the lithium batteries. We can provide an alternative and maybe redirect some of that lithium capability to the other high demand usage areas that we just can't really support with regard to having a kinetic battery in your electric vehicle. Probably not a good idea. With that, that's the end of my presentation, and thank you all for the opportunity to introduce you to our kinetic batteries.
Thank you so much. Next up, we have Cryostone.
Yes, hi, thank you very much. So first off, I'm Nikki Skukert for Cryostone. I'm the CTO and one of the founders of the company. And I just want to say thank you. We're so honored to be chosen for this prize. It means a lot to us, and the money, of course, is going to be very useful, but the networking opportunities are also coming at the perfect time for us. So, next slide. So our company is starting with the lowest cost current electrical storage method today, which is compressed air energy storage. And we're looking to address its two fundamental limitations. That's load round trip efficiency and geological constraints. On the left, you can see the large scale salt cavern, which is required for traditional systems, and it's huge. So that means that the capacity of these systems also needs to be huge. With our Cryostone system, we're able to go way smaller at 1/1000th of the scale and more than double the efficiency. So you can kind of see the two little pixels there within the magnifying glass. That's us to scale. And if we needed, we can also scale back up to 1000 megawatt hour. We can also do it gradually over time, getting some deployed capital benefits in there for anyone that doesn't need massive amounts of storage initially. So our middle diagram shows us how we use our excess power, and we're using almost any commercial off-the-shelf compression and expansion system. We're also able to retrofit existing generators and turn them into air compression vessels that we then take, and we use our highly efficient proprietary thermal storage system that behaves fully adiabatically and is what gives us more than double the round trip efficiency for the system. It also performs a very important function that allows us to cryogenically cool then and compress the air, which is why we're no longer using huge underground caverns for storage. Instead, we're delivering a single vacuum insulated steel tank that's basically full of rocks. Everything is off the shelf and currently manufactured. The only novel and patent pending technology here is what's detailed in that red box. And we have a lab scale system that's been demonstrated with over 20 charging and discharging cycles that has given a cyclic steady state to prove this out. All right, so next slide. So I think, one of the things that was most critical here is that, yes, this can be made entirely in the US. Again, we're just tanks and rocks. That makes us incredibly flexible, modular, and scalable, and also means that our materials are much more than 90% recyclable at end of life today. I think we're just being conservative saying that it's not 99%. Our, again, supply chain, completely mature. We're completely independent from any foreign country, and our ability to charge over 4 to 6 hours is vastly understating our capacity. We can handle 2% of our rated capacity for short durations. We can also handle as high as 300% of our rated capacity for short durations. So 8+ hours is not an issue. 24 hours is not an issue for us. We do think that we are significantly lower cost than any other storage technology that we've seen on the market, primarily because of our ability to deliver incredibly low storage aspect cost of this system and integrate with existing capital. And all of our components have a proven 30-year system life in other environments, significantly more rigorous than what we're currently going to be using them for. Again, that also gives us intrinsically safer to operate because we're not hot compressed air, we're cold compressed air, and that's also why we perform higher at lower temperatures. So next slide. All right, so looking at how our performance stacks up to the competition in this graph, on the y-axis, we're showing thermal energy removed, and on the x-axis, that's the duration and time. The first thing you'll see are the blue squares. That's the theoretical maximum. That's where we want to be. And our black diamonds there, that's the results from our lab scale system. And they're coming very close to following that beautiful S-shaped, almost step change curve. And that's why we're so excited. When you compare that to the gray triangles, which is the state of the art, they're a much flatter curve away from the maximum. And that's how we're able to preserve almost 95% of the thermal energy compared to around 30% for the state of the art. So what's next for us? Our next steps are looking to get an engineering study done for our full-scale system based off of our current lab scale results. We have already issued a request for proposal to some companies, but we're still considering potential partners here. We're also looking for anyone interested in a first-of-kind project. Minimum of 2 MWh is our initial capacity. Power requirement is completely negotiable. We've also initially planned to use any generic compression and expansion equipment or retrofitting existing equipment that's available, but we'd be incredibly excited if there was a partner in the space that's willing to work with us. And additionally, we could benefit from the expertise of anyone who's in the electrical integration area. So if you do feel like this is something that's interesting, my email, nikki@cryostone.com, and check out our website as well. So, thank you.
Thank you so much, Nikki. All right, up next we have Rondo Energy.
Good morning, good afternoon. Thanks for having us. Go ahead and hit the next slide. So I think Daniel did a great job. We're clearly competitors in this space. Earlier, just talking about the need and the application. So I'm going to try and cover some different topic areas. I think one of the interesting things folks don't always recognize is that industry is 36% of global emissions. And of that, 3/4 of that, or about 25%, is from on-site industrial process heat. And so industry is in the largest portion of global CO2. And there's really not been cost-effective solutions for decarbonizing industry to date. Go ahead and hit the next slide, please. And what industry really needs is continuous heat. Most of industry is running 24/7, providing processing, manufacturing products. And so when you're designing a storage system, you need to design something that can deliver heat continuously while charging intermittently. Renewables have now gotten cheaper than natural gas in most of the world, large parts of the world. And here we show a traditional solar charging shape, mostly because it's easiest to visualize, but the same idea applies for charging from wind or from the grid. Taking electricity when it's available and when it's cheap, storing that and delivering it as a drop-in replacement for industry. Next slide, please. When we think about industry, there's kind of 3 critical requirements when we talk to them as customers. One is you have to be extremely safe. The industry is extremely safety focused. So, solutions that have runaway thermal issues of, catching on fire, or liquids that might freeze or spill and catch fire, like those are going to be fundamentally really hard to integrate into industrial sites. Also, industry does need very high temperatures. And there's a big chunk of industry that needs steam. Which is a lower temperature. But one of the major things that we see in the space is that, oftentimes the end use temperature can be quite a bit lower, but those existing sites are using very high temperature for how they distribute the heat across the space. And so a major the major requirement is being able to drop in into that existing distribution system. So, maybe they're only using 10 PSI steam at the end use requirement, but they're distributing 150 or 300 PSI through all of their steam headers. And so being able to meet that high temperature for the high temperature steam or for calcination is really important as a drop-in replacement. And then I think this last point is actually really where Rondo is focused. So this proven reliability and durability. So one of the most important things for innovation is, and for decarbonization of industry, is the ability to scale and deploy rapidly. And a major component of that is getting to commercial, bankable technology as quickly as possible. And so on this point, Rondo has really focused on using existing materials that have 100 to 200 years of proven history, and that we're relying on existing industry to scale. So there's no rare earth materials in our systems. We're not doing material science innovation. And that's really important and a really critical driver. When our co-founders down selected to the technology and the materials that we're using, that was the primary consideration. Being able to get project finance to deploy projects for what is going to be a very large capital deployment of both the solar and the wind and then the heat batteries themselves is critical to the cost effectiveness and the ability to hit 2025 and 2030 goals for these companies. Most folks don't want to invest, project finance until they've seen 10 years of operating history on new materials. And so that's a critical consideration when you're considering innovation. Next slide, please. So to hammer on that, on the left is a traditional heat metal treating oven. Those electric resistance heaters have been used in that space for over 100 years. There's a well documented manufacturing and background on how they perform and what their breaking and life point is and how you operate them. And then on the right is a blast furnace brick used in the steel industry. And Daniel touched on this a little bit, but this existing material has been used for heat storage for over 200 years. All of our innovation is how we've integrated these two core components into a new system that's applied in an innovative way and in a novel way, and really is relying on that idea that renewable electricity has gotten so cheap. And the materials are low cost, proven, and they're available at giant scale. So we're not having to develop any sort of new supply chain. There's no shortage on the mine like there might be for lithium. The availability of the supply of these materials on both cases is available to hit the 9 terawatts of demand. Next slide. So our heat battery takes electricity. We use the resistance heater to heat up a stack of bricks, heat those bricks up to the temperature for the target application. We'll blow air across those bricks. That air is delivered as hot air for a drying or a calcination application, or we'll blow that hot air across to traditional heat recovery steam generator, a boiler. One of the major things that we're doing is we're intentionally doing as little that's innovative as possible on the material science front. So our bricks, our heaters, our boilers, we're sourcing from existing suppliers, and we're integrating them in innovative and novel ways. And really that integration and the design is about designing for a 40-year life for both the heaters and the bricks and the boilers, low O&M, predictable performance, and low installation and cost. And it's very high efficiency. I think I like to point out there that we're circulating just air. That's our working fluid. There's no argon atmosphere. There's nothing that's going to thermally run away. There's no risk of freezing or spilling or any of those things. Back to the safety point. Next slide, please. And so, oh, that's funny. There is half of a shot of our RHB 100. So we're deploying systems commercially today. Our website has our data sheets. Please reach out to us if you have any questions. Thank you.
Thank you. All right. Teams.
Can you hear me all right?
Yep.
Awesome. So hi, my name is Ben Hoffman. I'm the VP of Business Development for Thermal Mechanical Energy Storage LLC, or THEMES for short. You can go ahead to the next slide. So THEMES was started from the oil and gas industry by Dr. Ram Shenoy and Dr. Ashok Krishna. Ron was the former CTO at ConocoPhillips and Ashok, the former VP of Technologies at Chevron. Dr. Steve Shimana and Dr. Bhavani Ragaraman both designed and optimized process plants. And our main goal is to achieve geological scale renewable energy storage using thermal and mechanical solutions. Next slide, please. So if you look at existing geological systems, you will see Huntorp, Germany and McIntosh, Alabama. Both of these plants are still operating today and operate off of diabatic CAS. However, they were never duplicated due to the use of natural gas, low RTEs, and the fact that they wasted heat. So next slide, please. So Theme solution is really simple. We're using proven adiabatic CAS on the surface, and our innovation comes on the geological storage side. So on the left-hand side there, you will see kind of our 5 megawatt initial design. And this we're hoping to scale over the next 5 years or so. And this will rapidly scale from 5 to 100 megawatts for a really basic system. So you'll see basic compressors, basic turbines, basic water stores, a TES, and then the CAS in the center will be the subsurface storage. And on the right side, you will see kind of our subsurface innovation. So I touched on it a little bit before, but our team comes from oil and gas and has spent kind of the past 5 years working in the energy storage space, looking at how we can overlap carbon-free, long-duration energy storage with the oil and gas world. And what we came up with is storing air in the saline aquifer zone. So you'll see where that 2R is where the hydrocarbon zone will be. We're going to completely plug any existing hydrocarbons down below. We will then produce water for a couple months before creating an air bubble in the saline aquifer zone. And so what this does is it allows us to compress air down to the saline aquifer zone and then pump it back up and bring that air through a traditional expansion turbine to generate electricity and essentially provide a near zero marginal cost of storage. And so in existing systems where you had a solution mine cavern or in or any solution mine hard rock that would drive up the cost, our geological solution is about 100 to 1,000 times cheaper due to using existing wells, not needing to drill any new material, and being able to use that saline aquifer zone. So next slide, please. So our initial focus is going to be on California. The main reason for this, on the left-hand side, you'll see a CAISO duct curve, which I'm sure everybody here is very familiar with. But we see kind of 3 intersecting challenges in the state of California. So first, it's managing that growing inventory of idle wells. There's roughly 35,000 idle wells throughout the state of California, which could potentially be emitting fugitive methane emissions. This falls as a liability on any oil and gas operators' balance sheet. And if they cannot plug and abandon them, it falls onto the state. And so there's a huge liability cost on decommissioning these wells. And rather than abandoning those, we see an opportunity to repurpose them for energy storage. Through the state of California, I just touched on it a bit, massive idle and orphan wells throughout the state, as well as 100% renewable energy target by 2045. And so in order to deliver that reliable and resilient power, you need a solution at 100 plus megawatt scales. And then looking at California utilities. So there is a state target mandate of 15 gigawatts of capacity by 2032, 2 gigawatts of which they're looking for long duration energy storage of 8 plus hours. We're hoping to build out a 5 megawatt shortly, and that can rapidly commercialize up to 100 megawatts. And so that helps California meet their renewable power portfolio. Next slide, please. So to touch a little bit on just kind of our path to commercialization, where we stand today, we will be applying for CEC grants over the next year and be completing our subsurface testing. So once we have demonstrated that we can inject air into that saline aquifer zone and bring it up to provide power, then we will have a proven surface system with a demonstrated subsurface. We hope to begin 5 megawatt construction middle of 2024 and have a 5 megawatt operational plant by the beginning of 2025, possibly by the middle. We currently see an LCOS for 100 megawatt scale plants, which we hope to deploy by 2027, of around 10 cents per kilowatt hour, and see a direct pathway to 5 cents per kilowatt hour with just optimizing the system and the turbines. Next slide, please. So really what Themes is looking for right now, as I'm sure similar to everybody on this call, is both company investment to drive initiatives, project capital to build out these commercial facilities. And in terms of searching for partners kind of in this energy storage space, looking for any thermal energy storage suppliers that we could look at tying into the CAES system, and any energy storage companies looking to access the subsurface, because as I said, we specialize in the geological components for thermal and mechanical solutions. And if any interest in any of those, my email isn't on there, but you can reach me just at ben@themesllc.com. Thank you.
Thank you so much, Ben. Next, we have Cache Energy.
Perfect. I don't think I can get myself on the video. I'm disabled, but it works. We'll just jump in. So I won't spend a lot of time, talking about the need of storage. I think it's fairly well established by far, but we are taking slightly unconventional approach as we are storing energy in a solid fuel. You might have to click, Rebecca, a little bit. So we call our solution future fuel. Next slide, please, because it's very similar to coal, but without consequences. Keep clicking. It's still clean and safe. It's still very low cost. Almost every country in the world is self-sufficient in the material, and it can use all the existing infrastructure that fossil fuel built over decades. Next slide. So it's a fairly simple, well-known reaction since 1900s. Calcium hydroxide is heated to form oxide and steam, and that chemical reaction stores energy. The reverse reaction of steam and calcium oxide is exothermic. So calcium hydroxide is formed back and heat is released. And we can keep doing this reaction back and forth. The temperatures up to 550 degrees Celsius is reached, and under normal ambient steam conditions. Can you keep going? So on the system side, we store our materials separate from the reactor, and the pellets flow through the reactor, release energy, and are stored separately out once they're discharged. So we can keep shuttling back and forth between the two silos, storing and releasing energy. The pellets are roughly $100 a ton, so 20 cents per kilowatt hour, and this includes raw material, processing, everything taken together. Everything is at room temperature, even in the charged state. So all we are looking for to store this material is 4 walls and a roof. That's all. So when we scale at just 20 cents per kilowatt hour in terms of energy capacity. And that is one of the inherent differentiators for us. If we keep going, Rebecca. The other thing is location dependence. So once the steam pressure is fixed inside this chemical reactor, the upper limit of temperature is fixed. So 550, 560 degrees Celsius is the max, the temperature the reaction will occur at. So it's almost like an inherent thermal switch. We'll never have a thermal runaway. For example, fossil fuels, the higher the temperature, faster they burn, which would not be a case in our technology. One other thing to note is transportability. Since these pellets, even in charged state, are at room temperature, and once charged, they can store the energy for over 6 months without any self-discharge. We can store energy at one place and transport it somewhere else very safely, just like coal. So transportability and location dependence are two very key features of ours. If we keep going, Rebecca. Just one thing to note is energy density. We are not heating, cooling down something. We are actually doing a chemical reaction. And for that reason, we see much higher energy densities. Just, from physics principles, chemical bonds store much more energy than sensible heating. If we keep going. And this is one interesting slide I wanted to bring to your attention, is a very first principle look at why we call ourselves ultra long duration scalable technology. Any storage technology can be broken into two parts: energy components and the power components. And the total cost would be the summation of both. And the H here is basically the duration. the duration of energy storage. What happens when you start increasing the duration of energy storage, the power components do not play as much role in a total cost as energy component. Energy component do not scale with duration, meaning that for every unit of capacity that you add to your system, this is a fixed cost that any system has to incur. A very crude example would be the gasoline in our car, right? So in our case, the energy component is basically storage material in the silo. If we keep going, so the storage material is roughly $100, $200 a ton. So 20 to 40 cents per kilowatt hour. And as I said, it includes the raw material processing, everything included. And the silo cost is practically zero, because all we are looking for is 4 walls and a roof. Anything that can prevent my material from heavy rain pour or steam passing through it. So it's almost like coal. Coal doesn't lose energy just because you have stored it, right? Unless we burn it. So very similar principles. But if you start comparing, other storage technologies, the raw material cost itself and the fact that it's hot and corrosive and needs a containment and insulation around it, the energy cost is significantly higher. So sometimes, it's easy to see why a material is cheap and makes sense, but what we shouldn't forget is where is that material being stored. So it's not just enough to say that we have a cheap material, but if the cheap material is at like 1,000 degrees Celsius and needs a containment around it, that adds up very quickly. Next slide, please. So where we are, we have completed this. There is the material part. So we have proven our material out, that it discharges over like hundreds of cycles. Then the next task was to put these material in a reactor and demonstrate that we can put in and heat in and out efficiently. That's what we did. And we also built a flash heating demonstration unit. It basically what it does is like produces hot water very quickly, like within a few seconds. And finally now we are designing and about to fabricate a 100 kilowatt system. So ultimately, this is how our market, approach looks like. We are targeting long duration energy storage and coal repurposing. We are in talk with one of the leading energy companies where we are trying to see how these pellets can be a drop-in replacement of coal in the shut coal power plants. So that is our like North Star. But if you start thinking about the barrier to entry in the market in terms of how much money this requires, what is the minimum system size that generates the first revenue, we see lower hanging fruits. So if you keep going, Rebecca, twice, higher temperature industrial heat is one. And even before that, we see less than 300 degrees Celsius heat being a big market, because, less than 500 is like 70-80% of industrial process heat demand. Less than 300 degrees Celsius is half of that. So a significant chunk of demand at a much lower temperature exists. And that's where we aim to start, but then climb our ladder up to the long duration energy storage market. And we are really excited to be selected, and thank you very much for your time.
Great, thank you so much. Our next group is Thermal Battery Corporation. And they were unable to make it. I couldn't remember. I'm going to share a quick video from them, but I believe I have to make a quick. Here we go. I'm gonna try sound this time.
Hi, I'm Dr. Ashegun Henry. I'm a professor in mechanical engineering at MIT. I'm the original inventor of thermal batteries, and I'm the founder and CEO of Thermal Battery Corporation, abbreviated as TBC for short. Thermal batteries are grid-scale rechargeable batteries that have an estimated levelized cost of storage below 4 cents a kilowatt hour. Now that's cheap enough to enable full penetration of renewables onto the grid. The technology involves converting electricity to extremely high temperature heat above 2000 degrees Celsius, and then it's stored in graphite blocks that are held in an inert environment. When electricity is desired, liquid metal is mechanically pumped through the storage blocks to retrieve the heat, and then the light emitted by the glowing white hot piping network is converted back to electricity using thermal photovoltaics, abbreviated as TPV. I've been developing this technology in my research group at Georgia Tech and MIT over the last 10 years, and we have pioneered 3 important technological breakthroughs that now render the technology feasible to pursue commercially. The first is liquid metal pumping at extreme temperatures. The second is high efficiency TPV cells. And the third is a patented approach to preventing deposition of the hot emitter material onto the TPV cells. If you want to learn more, please check out the TBC website, thermalbattery.com, and watch the explainer video at the top.
Right. And then our last finalist was Energy Solutions. I know that we do have them on the line, but I think we're going to play the video unless you'd like to say anything. Please feel free to pop on. I'm going to go ahead and jump into that video though.
Hi, I'm Ayub Momin, the founder and CEO of Energy Solutions. I'm a former senior scientist and program manager at Oak Ridge National Lab.
I'm Ahmed Abouhiba, a former R&D staff at Oak Ridge National Laboratory.
We are the inventors of ground-level integrated diverse energy storage system, aka GLISE, at Oak Ridge. It was a great success story, and technology later on was licensed by a company. GLISE is an excellent utility-scale energy storage technology that combines the benefit of pumped storage, hydro, and compressed air energy storage. We participated in DOE's Energy Core program. After conducting more than 75 interviews with the stakeholders, we identified the shortfalls of GLISE and as a utility-scale energy storage. Then we asked ourselves, how can we address these shortfalls? After we spend a lot of time weighing our options, we come up with a novel, economical, long-duration energy storage solution that we are proposing here. This solution has 20 times higher energy density than our previous technology and uses abundant material, enabling us to be 90% less expensive than regular lithium-ion batteries. Our proposed technology and components can last for more than 30 years and store electricity for multiple days. We are so excited to put our novel approach or novel technology here to test in American-made challenge. Together, we can do better. Thanks.
Okay. And that is all of our winners. Thank you so much to all of our panelists for being so time conscious. These were all really great pitches. Ben, I don't know if you want to hop on and say anything here.
Yeah, I finally have my video on, my computer updated. So thank you all so much. This is fantastic. I'm personally just so excited now seeing all 10 of these winners. You guys gave some great presentations. I just wanted to include a couple links up here. The only one with a QR code is the Storage Innovations 2030 website, but check back there for more updates on the broader SI 2030 initiative. And more generally, if you want updates from the Energy Storage Grand Challenge or the Office of Electricity, both of the links that are included on the screen have available boxes where you can put your email address and you'll get updates with future announcements, RFIs, and other news coming from the Department of Energy. So thank you all so much. We'll be in touch over the coming weeks again with more about this congressional report and including your technologies there. But one more congratulations to everyone. Thank you all for coming today.
Yes, and just to reiterate, we did record this presentation. It will be posted on the HeroX website for this prize. Thank you all for tuning in.